Okay, so here's what's remaining for the semester. 4 chapters, 3 on optics, 1 on relativity. And this week, there'll be chapters 32 and 33, which are on geometrical optics. We studied light last week, but only light in empty space, light in vacuum. And we found from the electromagnetic theory how electromagnetic waves propagate in empty space. Well, optics is the science and engineering of light interacting with matter. So a lot of what we learned last week about electromagnetic waves in empty space will also apply to light interacting with matter, but there will also be some changes, some differences. So we start with these 2 chapters on geometric optics. Now, light is an electromagnetic wave, and it has several aspects. First of all, there's the direction of motion. We learned last week that in empty space, light just travels in a straight line. And the electric and magnetic fields oscillate perpendicular to the direction of motion. Well, okay. That will also be true in some kind of materials. So one aspect of optics is the direction of motion, and that's called geometrical optics. But the other aspect of optics has to do with the oscillating fields, the electric and magnetic fields. And that's called wave optics. So in geometric optics, we can sort of treat light as just traveling in straight lines, and we're just analyzing the geometry of those lines of propagation. But there's more to it than that, and that's going to be the subject of chapter 34, wave optics. All right, so the main thing I wanted to do tonight was go over some problems from the assignment, which is due Thursday. So let's look at some of these problems. By the way, can you hear me?
Yes.
Okay. All right, then. Here's one of the homework problems. There's a metal cup, which is in the form of a cylinder with radius r, or diameter 2r, and depth d. And your eye is located here, where you can just see the far edge of the lower side of the cup. But you can't see, for example, the center of the cup, because light coming from the center of the cup would go up in this direction. Or maybe, and that would not go into your eye. Or if it was just barely coming towards your eye, it would travel in this direction, but it would not go into your eye. So you see, with your eye located at this position, light from the far end of the lower surface will come into your eye, but light on the lower surface, and in particular at the center of the lower surface, would not come into your eye and you wouldn't see it. Well, that's when the cup is empty. So light just travels in straight lines. You know, it's just traveling through the air in a straight line. But now fill the cup with water. Well, when the cup is full of water, light doesn't travel in straight lines because of refraction. So in fact, you could have light which travels into your eye from the center of the lower surface, from the little red dot. So let me put it in red. Whoops. It's not quite what I wanted. I guess I can't do it that way. It comes up and bends. The light doesn't follow a straight line because of refraction. Now we know the equations for refraction. So Snell's law says n1 sine theta 1 is equal to n2 sine theta 2. So n1 will be in the air, and the index of refraction is, we can just approximate it by 1. n2 would be in the water, and the index of refraction of water is 1.33. So you see, sine theta 1 and sine theta 2 will not be equal because n1 and n2 are not equal. Now these angles, theta 1 and theta 2, are angles of the ray of light with respect to the normal direction of the surface. The surface is here because we fill up the cup all the way to the top. So that's the surface where there's the discontinuity of index of refraction going from n2 to n1. Now, so theta 1 will be this angle. It's the angle between the ray of light, or the direction of the light, that's the direction of the light here, which is relative to the normal direction. The normal direction is perpendicular. So this would be the angle theta 1. Now the angle you're given is alpha. So theta 1 is 90 degrees minus alpha. Now, if we think of the light going in the other direction, going in from air into water, when light goes from air into water, it's bent toward the normal. So the direction of the light ray would be bent towards the normal, and it would have this angle theta 2, which is again the angle with the normal. The normal is perpendicular to the surface of the water. The surface of the water is vertical. So this would be the angle theta 2, just hitting the red spot. So that if I turn things around and I view the light coming from the red spot, hitting the water surface and bending, in this case, away from the normal because it's going from a higher density to a lower density, it will go in the direction of your eye. So again, here's the direction of your eye at the angle alpha. All right, so we have this picture. We have the radius, this distance, the depth, this distance. We have alpha. Now what's given? Well, what's given is the radius. So what we know is the radius. That's one thing we know. Another thing we know is the index of refraction. The index of refraction is 1 above the surface and 1.33 below the surface. So that's the information we have. We don't know alpha, but we can relate alpha to the depth by trigonometry. If I look at this little triangle here, that triangle has angle alpha. This angle is also alpha. The opposite is D. The adjacent is R, or actually 2R. So the tangent of alpha is D over 2R. So here are the equations we have. N1 sine theta 1 is N2 sine theta 2. Okay. Also, theta 1 is 90 minus alpha by this picture. Theta 1 plus alpha is 90, so theta 1 is 90 minus alpha. So let's write Snell's law. N1 is 1, N2 is 1.33. So the sine of 90 minus alpha, that's the same as the cosine of alpha, is equal to N2 sine theta 2. And we know N2. And then, again, by looking at this triangle, the opposite to alpha is D, the adjacent is 2R. So the tangent of alpha is D over 2R. And we need one more equation because we sort of have three unknowns here. D is not known, alpha is not known, theta 1 and theta 2 are not known. Well, we actually have quite a few unknowns. We need one more equation. And if I look at this little right triangle here, that's this triangle, that will relate theta 2 to D. In this right triangle, the opposite to theta 2 is R, and the adjacent is D. So the tangent of theta 2 is R over D. So I have here three equations, various unknowns. I guess we have four unknowns, but we also have this fourth equation. No, that equation has disappeared. In these three equations, I have three unknowns. I have three equations here, and there are three unknowns. Alpha, theta 2, and D are all unknown. Well, if I have three equations with three unknowns, I should be able to calculate all the unknowns. Now, what the problem asks for is D. So I want to solve these three equations and end up with the value of D. So now the rest of the problem is to solve for D. So just, at this point, it's just math. It's just a bit of algebra or using trigonometric functions. Now, to approach this, the first thing I can do is eliminate D. By this equation, let's see. If I bring R up here and I put tangent alpha down here, I'll have R is equal to D divided by 2 tangent alpha. 1 over tangent alpha is cotangent alpha. So this equation, by a little bit of algebra, multiply both sides of the equation by R, divide by tangent alpha, I get R is D divided by 2 times cotangent alpha. And by this equation, R is equal to D tangent theta 2. Now I can cancel D, both sides of the equation. So you see I've eliminated D. Now eventually I have to calculate D, but in the meantime, I've eliminated D, and I can reduce the equations to just two equations for the angles. For one thing, I have, okay, cancel the D's, then I have cotangent alpha is 2 tangent theta 2. So there's one equation. And now this equation relates alpha and theta 2. Cosine of alpha is 1.33 sine of theta 2. All right, so I've eliminated D from the equations, and now I only have two equations with the unknowns alpha and theta 2. All right, so I should be able to solve these two equations. Let's try to solve for theta 2. Because by this equation, if I know theta 2, I can immediately calculate D. You see, D, if I multiply both sides of the equation by D and divide by tangent, I find D is R cotangent theta 2. So what I'm looking for is D. Well, once I get theta 2, this equation will determine D. So let's take these two equations and see if I can eliminate alpha and just get one equation for theta 2. All right, so N in this region is 1, N in this region is 1.33. And for the direction with total internal reflection, whoops, I don't want that. Sine theta is 1 over N. That's the equation for total internal reflection. The total internal reflection really concerns light going in the other direction. You know, if light was coming from below, hitting the surface at the angle for total internal reflection, all the light would be reflected and there wouldn't be any light coming into the upper region. So total internal reflection really refers to the other direction for the light. Light comes from the below, hits the surface, does not emerge into the air if the angle is greater than the angle of total internal reflection. It just all reflects. But the equation Snell's law is valid no matter which direction the light is going, whether it's going from the water into the air or from the air into the water. Both cases satisfy Snell's law. So this equation, arc sine of 1 over NW, will be the characteristic angle for the edge of this bright region. So let me draw a picture, another picture. We have light coming in from the sky in all directions. But where it hits the surface, it's bent down. It's bent towards the normal because of refraction. Because of Snell's law, light coming in from the horizon will be bent down to an angle of theta W. Now that's the angle between the ray of light and the normal. But if you think about the geometry here, that's the same as the angle from the ray of light to the vertical direction. The normal is vertical. So you see here I have parallel lines cut by a line, the two angles will be equal. So this angle, which I calculate from optics, is the same as this angle, which is the angle of the cone of light. So the entire sky is compressed into a cone, and you see that in the picture here. This is the entire sky. As it would be seen, actually, the photographer had to be below the diver, but this is as it would be seen by the camera below the diver, which has taken this picture. All right, so that's an example of Snell's law, but it's also an example of total internal reflection, which is just a special case of Snell's law. Here's the next problem. It says convex mirrors are often used as side view mirrors on cars. A warning is written on the mirror. Objects in mirror are closer than they appear. If you've driven an SUV, for example, and looked at the rear view mirror, the one that's outside the car, not the one inside the car, you probably see this statement: objects in mirror are closer than they appear. So let's suppose the radius of curvature of the mirror is r, and that's given, approximately 15 meters. And let's suppose that a car is a distance d behind the mirror. So you're sitting in the SUV and there's a car behind you at a distance d. And that distance is given, approximately 11 meters. Find the perceived distance and the magnification of the image of the car. So this is a problem where you're supposed to analyze the image formed by reflection in a mirror, but it's not a plane mirror, it's a convex mirror. Now, there's a discussion of this in the book, and if you look at figure 32.26, it shows exactly this situation where you have reflection from a convex mirror. But instead of just copying the picture from the book, let's make the picture here. Here's the mirror, and it's convex, so it's a diverging mirror. And here's the object, it's a car. Well, instead of drawing a car, let me draw a little arrow. And so I'll analyze the rays of light coming from the tip of the arrow. There'll be an image. And this will be the image. It'll be on the other side of the mirror, just like it would be if I had a plane mirror. But it won't be identical to the object because I have a curved mirror. So to figure out the size and distance of the image, I have to analyze rays of light coming from the tip of the arrow. So, you know, you could think of the arrow, you can think of, this is the car, remember. I can think of this as, well, I wouldn't say the car is self-luminous. There's just reflected light coming from the car, or rather coming from the arrow, or rather coming from the tip of the arrow. A ray of light coming from the arrow in the direction of the axis of the mirror will reflect from the mirror and come off in this direction. The law of reflection holds where it reflects, so there are equal angles. There are equal angles between the incident ray and the outgoing ray coming from the tip of the arrow. Now, for a convex mirror, if it's parabolic or if it's spherical but approximately parabolic, has this focal length. Namely, the outgoing ray comes from the direction of the focal point the focal point over here, the focal point behind the mirror. Now, I know the focal length. Well, I can really think about two focal points. There's a focal point here to the right of the mirror, and there's also a focal point here to the left of the mirror. And the characteristic of reflection from a spherical mirror, or better yet, a parabolic mirror, is that light parallel to the axis appears to be coming from the focal point behind the mirror. In other words, it's traveling in the direction away from the focal point on the other side of the mirror. All right, what is this focal length? Well, for a spherical mirror, the focal length is the radius of curvature divided by 2. So this is a result which is given in the book. This is a result that you have to use whenever you're concerned with convex or concave mirrors, the relation between the focal length and the radius of curvature. Well, this focal length will be r over 2. R is given. So this focal length is, well, approximately 15 divided by 2 would be 7.5. So this is 7.5 meters. And this is a little over 11 meters. So the object is farther away from the mirror than the focal point. All right, that's one of the rays of light coming from the tip of the object. Now let's draw another ray of light coming from the tip of the arrow, but this time not coming in the direction parallel to the axis, but coming towards the very center of the mirror. You see, by the law of equal angles, it'll reflect off at the same angle. So here's the ray of light drawn in red. Not that it's a different color, it's still this color of the car, but just I drew it in red so that you could see the difference between that and the other ray that I considered. This ray comes to the center of the mirror and then reflects off and comes out, obeying the law of equal angles. So you see, what I have here is I have light coming off in this direction, and I have light coming off in this direction. And if I had a camera with a piece of film over here, the light would look like it was coming from the image. The camera couldn't tell the difference between light coming from the mirror and light coming from the image where the mirror is not present. So that's the image. And if I trace these rays, if I trace these outgoing rays back to the other side of the mirror, I find they cross at this point. So that's the image. It's what's called a virtual image. It's a virtual image because there isn't actually any light there. It's on the other side of the mirror. You know, it's on the other side of the mirror where everything is dark. But the light that reaches the film, or think of this as your eye, appears to be coming from this position. So that's what's called the image. And what we're interested in is the distance from the mirror. So that would be d sub I. Here's d, or sometimes this is usually called DO. DO for object. It's the distance from the object to the mirror. That's the 11.3 meters. Here's DI. You know, for a plane mirror, DI is equal to DO. That's for a plane mirror. But for a curved mirror, DI is not equal to DO. One thing I'm trying to calculate is that DI. So that's the perceived distance. It says objects in the mirror, that is to say this image, is closer than they appear. Now, I also want to calculate the magnification. Yeah, this objects in mirror are closer than they appear is a little bit, requires a little bit of thought as to what that means. You see, if this were a plane mirror and you saw this object, this image, you would assume that the object was right here. Because for a plane mirror, DI and DO are equal. So if you see this and you see an image and you say it's an image and you're thinking in your mind that this is a plane mirror, you would think that the object is just right here, a lot closer than it actually is. So objects in mirror are closer than they appear. All right, so a little confused by this statement. Oh. Well, okay. Let's calculate DI. What is DI? Well, you have this equation, which is valid for all kinds of reflections and also for lenses. 1 over D plus 1 over DI is equal to 1 over F. Or I could say this is 1 over DO plus 1 over DI is equal to 1 over F. And that equation is valid for both reflections and for lenses. But it's not as simple as it looks, because you have to take into account the sign conventions. In the case of a virtual image with a mirror, the focal length is defined as negative. So the focal length is negative R over 2, or 1 over F is negative 2 over R. So you have to be very careful to study the signs. And again, if you look at figure 32.26 in chapter 32, there's a paragraph which analyzes this and points out the signs, the somewhat tricky signs that you have to take into account. Make sure I got the recording going. So here's the last problem in the assignment. You have a glass prism. So you see it's a piece of glass shaped in this form of a right triangle. Of course, you have to visualize this in 3 dimensions, so this is just a side view of the prism. And you have light incident with this direction. Theta I, that's relative to the normal to the surface where it's incident. So theta I is the incident direction. Now, as it comes into the glass, it will be bent towards the normal by refraction. So this ray of light will come off in this direction. And there'll be another angle here. And then when it hits this other side, there'll be reflection and refraction. But what you're asked about is, when will it undergo total internal reflection? So in other words, you want it to come off with a reflection, which will come off in this direction. and all the energy should be reflected. No energy transmitted into the air. No light coming off in this direction. That's the condition for total internal reflection. And the question is, what's the minimum value of theta I for which that will be true? In other words, if you make theta I too large, then you'll get total internal reflection. You want the very smallest angle, theta I, for which you get total internal reflection. If theta I is any amount larger than that, you'll also have total internal reflection. Now, what information are you given? Well, you're given the angle of this prism, 85 degrees. And one more piece of information, you're given the index of refraction of the prism. Unlike water, water always has index of refraction 1.33. But glass is different because glass has different compositions. So the index of refraction of glass is not always the same. Glass could have an index of refraction less than 1.5, or it could have an index of refraction greater than 1.7. It's usually somewhere between 1.5 and 1.7. It depends on what the material, what exactly is the material composition of the glass. But you're given the index of refraction and alpha, the angle of this prism. And what you're trying to calculate is the angle, this angle, for total internal reflection at this point. All right, so let's draw a bigger picture here. So here's the prism with angle alpha. And here's the incident ray. It undergoes refraction at the front surface and comes off with the direction theta 2, where n1 sine theta 1 is equal to n2 sine theta 2. n1 is the index of refraction in air, so that's 1. So 1 sine theta I is equal to n sine theta 2. So that is the refraction at the front surface. That's Snell's law. Sine theta I is n sine theta 2. Now the light will travel to the backside of the prism and reflect with equal angles. So it'll come off in this direction. And now let's draw the normal to the back surface. So here's the normal to the back surface. Let's compare that to the horizontal direction. So what's this angle right here? Because that will be the angle of incidence where the light ray hits the back surface. It'll be this angle. No, it'll be this angle. It'll be this angle. Let me put it in a different color. Try green. No, I already used green. Let's try gray. It'll be this angle. That's the angle of incidence of the light ray hitting this position, hitting this back surface. You see, it's the angle between the direction of the ray and the normal. Well, here's the normal, this blue line. So let's call that theta 3. So we'll call that angle theta 3. All right, so sine of theta 3 will be 1 over n. That's the condition for total internal reflection. Remember, total internal reflection occurs when the angle is the arc sine of 1 over the index of refraction. It occurs when light comes from a more dense material going towards a less dense material, like glass into air. Well, if the angle is larger than this critical angle, the arc sine of 1 over n, there won't be any escape into the air. It will just all be reflected. So we're looking for the angle or for the condition when theta 3 is the arc sine 1 over n. That's the condition for total internal reflection. Now that gives me 2 equations, but I have 3 unknowns. So I have to have another equation. I have to relate theta 3 and theta 2. And you see, theta 3 is a combination of theta 2 plus this angle. So theta 3 is theta 2 plus this angle. This angle is 90 minus alpha, because this angle is alpha. Here I have the horizontal line. Here I have the horizontal line. Here I have a line cutting horizontal lines. This angle has to be the same as this angle, alpha. And this is perpendicular to that line. So this angle has to be 90 degrees minus alpha. So I have theta 3 is theta 2 plus 90 minus alpha. So I have here, I guess, 1, 2, 3 equations with various unknowns. And what am I trying to calculate? I'm trying to calculate theta I. So I have to solve these 3 equations for theta I. All right, so let's see how we can do that. Oops, I didn't want to stop the share. I didn't really have anything more to say tonight. I didn't bring the results for the second exam. On the corrections exam, most students had over 90%. On the written exam, the average or the median score was less than 90%. I don't know exactly what it was. But anyway, you get some extra credit for doing the corrections exam. So you'll have to wait and see when your exam result is available at Long Kappa. Now, you know, your grade is not yet determined, because there's this homework assignment, 2 more homework assignments, and the final exam. So if you're not satisfied with your grade so far, you can still raise it. Just work on the final 2 homework assignments, plus this one, which is due in a couple of days, and then be prepared to study for the final exam. My understanding is the final exam will be cumulative. It will cover everything in the semester. So you might start studying for this final exam a little bit early and start writing down equations that you can use during the exam for an equation sheet. Okay. Any questions?